Hello, these are the solutions to Activity 9. Activity 9 covers our next chapter, Chapter 7. If you have recitation on Thursdays, you're going to do this activity before you see these concepts in lecture, so hopefully your TA will use this activity to introduce some ideas to you, and then lecture can hopefully make some more sense when we get to these topics. And then if you have recitation on Tuesday, they'll still just be kind of like a normal review activity. It's kind of short, so I don't think it'll be too long. So question one is about effective nuclear charge. Effective nuclear charge is the sort of idea that only the core electrons can really screen the effective charge in the nucleus from the valence shell electrons. So if you look at, say, the second row of the periodic tables, you look from lithium to beryllium to boron to carbon, nitrogen, oxygen, fluorine, neon, that as you look at these elements here, that they all share in common just having the 1s2 as its core. And then all the next 1 through 8 electrons for these atoms are valence electrons. So the valence electron count goes from 1 to 2, 3, 4, 5, 6, 7, 8 onward to neon. And so they all share having this 2 electron core. And really only these 2 electrons can screen the effective charge from the atoms. And so you go from having a relatively low effective nuclear charge. The effective nuclear charge is the Z, the nuclear charge. This is just the number of protons in the nucleus of the atom. So the Z is just the atomic number. So you go from 3 to 4 to 5 to 6 to 7, 8, 9 to 10 across the neon. That if really only these 2 electrons are dampening this charge, this is a positive charge. So you really just have 2 electrons getting in the way. So your Z effective is approximately equal to plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, plus 8. And then if you think about getting back to sodium, to the next element after neon, sodium then goes to having, a Z of 11, but then it has a much bigger core. So it has that neon core, 1s, 3s1. So it goes back to having a Z effective of about 1, matching that of lithium. So the effective charge being the same or similar to that of lithium is what's really giving the alkali metals their similar property. That they're all the elements that kind of now are restarting their effective charge of being a relatively low charge compared to the opposite preceding side of the periodic table, the noble gases, as having a really high effective charge and also having no room for more electrons. And so the effective charge is that repeating charge. This is where we get that periodic behavior, where we get from left to right. We go from having a metal, metallic element on the side of lithium to having a non-metal completely set of properties on the opposite side of the periodic table. So we have this increase in effective nuclear charge from left to right. So the effective nuclear charge increases left to right because our core electrons are constant as you proceed from left to right. And then our effective nuclear charge, let's think about the top to bottom trend here in a minute. So for left to right, at least we would say fluorine's going to have a higher charge than lithium, having a lower effective charge. And then what about our top to bottom trend? Um, think about how the core, as it grows in size, so as you go from having a 1s2 core to a 1s2, 2s2, 2p6 core, to then if you think of the core for the fourth row of the periodic table would be the argon core. So an argon core goes up to having the 1s2, 2s2, 2p6, 3s2, 3p6. So as you start getting this core, as the core electrons are moving further and further away from the nucleus, they're not screening as effectively. So our Z effective is going to have a slight increase from top to bottom. So as you go from down a group, you're going to see that the effective charge of say potassium is a little bit higher than sodium, is a little bit higher than lithium, because the core of potassium is bigger and it's letting more of that nuclear charge through, so it experiences a slightly greater effective charge. So our effective charge is going to be higher for lithium, or excuse me, higher for iodine compared to rubidium. So iodine should definitely be higher from left to right perspective than rubidium, but then iodine's higher than fluorine when we look at the top to bottom trend. So fluorine, bromine, fluorine, chlorine, bromine, iodine. Iodine in the same group as fluorine. Iodine is going to have a slightly higher effective charge compared to fluorine, and it's due to a the core electrons increasing in size, and that those electrons not dampening as much charge. So there's an equation that says our effective charge is equal to Z minus S. S approximately equal to the number of core electrons, but as those core electrons go bigger, not as effective. So S is basically as high as the, S is, has to be less than or equal to the number of core electrons. So the dampening can't be higher than the number of core electrons, but it could be less. As those core electrons are bigger, they don't screen as effectively. Which atom below has the largest atomic radius? So you can think about how two things impact the atomic radius. One of those would be the left to right trend of effective charge. So as you go from lithium on across, let's just look at lithium to fluorine, that our size is going to decrease with this comparison because we're going to a higher effective nuclear charge. And so that higher charge is going to pull those electrons in more closely. So this radius of lithium should be greater than the radius of fluorine. And so left to right, size decreases, left to right, but then size increases top to bottom. You could think, well, didn't the effective charge increase from top to bottom? But you're just using bigger orbitals. So as you go from top to bottom, you're just using bigger n orbitals, and as n increases, the size of the orbitals increases. The size increases top to bottom just because n increases and then size increases with n. And so which atom below has the largest atomic radius? So here let's try to reconstruct. So we have lithium, sodium, and then we have nitrogen and then sulfur here. So we have second row elements this way, and then we have two alkali metals. And so sodium is going to be bigger than lithium. From top to bottom, it's bigger. So answer can't be lithium. Lithium is bigger than nitrogen. So nitrogen is smaller left to right, decreases in size left to right. So nitrogen is smaller than lithium. And then sodium versus sulfur. Sulfur will be smaller than sodium left to right, size decreases left to right. So the answer here would be sodium. Select the atom in each pair that has the greatest size. So think about sodium. So think about having 1s2, 2s2, two-piece set of electrons, 3s being this size. So this is sodium. What if I remove this s electron? Do we think the size of the atom will increase or decrease? And obviously it's going to decrease. So if you take electrons away, we're going to decrease the size of that ion compared to the atom. So, and then this is for anything too. If you go from calcium to calcium plus to calcium 2 plus, that you're decreasing the size each step of the way. So calcium 2 plus smaller than calcium plus, smaller than calcium. So sodium plus, we're looking for the pair greater in size. So sodium is going to be bigger than sodium plus. Now if you add an electron, well, if I have, an atom of F, and I have my 1s2, 2s2, my 2p set of electrons here, and if I add one more electron here, that's going to increase the size of the orbital due to electron repulsions. So electron repulsions make anions larger. So adding electrons increases size due to electron repulsions. So we're decreasing size due to either decreased electron repulsion or just getting rid of our bigger orbitals from being used, like sodium plus just lost that 3s orbital, so definitely decrease in size. So F minus is bigger than F. Sodium versus fluorine, we just use our periodic trend. So sodium, lithium, fluorine kind of goes this way here. So like fluorine smaller than lithium, lithium smaller than sodium, so of course sodium is bigger than fluorine. Now, this is a really interesting comparison. What about plus and minus? For sodium plus, fluorine minus, notice F minus has 10 electrons. Notice that sodium plus has 10 electrons. So we had 11, lost 1, we had 9, added 1. So they're what we call isoelectronic. Isoelectronic means they have the same electron configuration, so they're both 1s2, 2s2, 2p6. And so if you have, those, 1s2, 2s2, 2p6, which ones do you think are going to be smaller, the one with 9 plus or the one with 11 plus? The smaller one's going to have the higher Z. The more protons you can pack in, the more you're going to draw those negative electrons in more closely. So sodium plus goes smaller, F minus is bigger. Okay, so notice F is smaller than sodium when they each have their neutral charge, but then if you add their usual charges for their common ions, fluoride becomes bigger than sodium plus because it has fewer protons to hold that same count of electrons in. So whenever we're isoelectronic, we're comparing the Z or the nuclear charge to the number of protons. So we're going to go sodium F minus, sodium F minus for our choices here. Number 4, what is the general trend and proper explanation of the first ionization energy from top to bottom of a column of the periodic table? So ionization energy is the energy required to remove an electron. So let's just think of this trend here. So we're going to lithium plus an electron, sodium plus an electron. Now, so I can write the letter K plus an electron, rubidium plus an electron. And so we got two things going on here. One is we can think of we have one main equation and then a couple of considerations. So the energy of electrostatic attraction, let's just keep this as a proportionality, is proportional to the Q1, Q2 divided by the distance of separation. And the energy of electrostatic attraction is when you have minus plus or plus minus. So negative electron, positive nucleus. And if you have negative, negative, plus, plus, and you get the energy of repulsion as opposed to attraction. So we get energy of attraction here with minus and plus. And so the greater the magnitudes of the charges, then the higher the attractive force between those particles. So the higher I can make these magnitudes of charge. So as Q goes up, the energy of electrostatic attraction goes up. So like the magnitude of the energy, it's really becoming negative. It's technically becoming more negative, but the magnitude of that energy attraction is increasing the greater the magnitude of charge. And then the closer we can make the particles, the higher their attractive force as well. So the closer you make the particles, so if you have two oppositely charged particles but they're a mile away from each other, that's not good. If you have two oppositely charged particles that are right on top of each other, that would be good for their energy of attractive force being a greater value. Okay, and so if you think of lithium plus, you'd be like, okay, lithium's good because we have an electron in a smaller orbit size, but the effective charge, though, is relatively low. So our effective charge is increasing top to bottom. So rubidium's is the highest for this group of elements here, but its size is, of course, higher. So how do you deal with the fact that we have the valence electron moving further away, so the D's going up, but the Q magnitude of charge is going up? The Q magnitude going up says the attractive force should go up. The distance becoming further away says it should go down. Now, the ionization energy trend from top to bottom is almost kind of flat, but to a general, if you inspect most of the elements in the periodic table and most of the groups on the periodic table, you're going to see that you get a slight decrease in the ionization energy from top to bottom. Slight decrease because the winning factor is the size. The size of the atoms are increasing with that same trend. And so despite the fact that the effective charge goes up a little bit, the size trend tends to win out if you inspect the chart, we'll do this in class, you can inspect all the groups in the periodic table and see there's a few cases where the charge trend wins out and the ionization energy increases from top to bottom. But the general trend is that it decreases from top to bottom with a slight decrease. So IE1 decreases from top to bottom because the atomic size is increasing. So the Z effective does increase from top to bottom, which would make you think that the IE1 should increase, but this turns out not to be the trend because you have two counter-opposing trends, and usually the size trend is what wins out. 5. Which statement is correct? The first ionization energy always increases left to right. So if you think of the left to right trend, so if you go lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. If you're looking at this trend here, your ionization energy goes up to beryllium, it actually drops to boron, then it goes up to the next three elements, and then it the ionization energy drops a little bit, and then increases to nitrogen, drops a little bit for O, and then increases towards neon. So you get this kind of behavior here of your I1s not increasing every step of the way. There's a little bit of a pattern to it. The pattern comes from the fact that we're removing electrons from different orbitals. So you're removing a 2p1 electron here, and then oxygen's removing a spin paired electron. And so you're just removing electrons from a higher energy subshell, so it takes a little less energy than beryllium because you're removing the 2s2 electrons. And then here you're removing a spin paired electron, so you get a little bit of a break in the trend from the orbital energies from what you expect. So the ionization energy does not always increase left to right. Electrons closer to the nucleus have a lower ionization energy than electrons residing in larger orbitals. Electrons closer to the nucleus should have a higher ionization energy because they're closer to the nucleus, so that D term being smaller. So you decrease the size of the attractive force, you increase the energy of that attractive force. The 2s electrons in oxygen have the lowest ionization energy of all of its electrons. If you look at an atom like oxygen 1s2, 2s2, 2p4, you can ionize each of these electrons. The hardest to ionize are the core electrons, so they require the greatest amount of energy. And so it's the core electrons that require the greatest energy, not the 2s. Compared to the first ionization energy, the second ionization energy of an element always requires greater energy. This is true. So if you let any element, if you go from some element M to M plus an electron that takes however much energy, M plus losing a second electron will always take more energy than the first element. So M losing an electron requires however much energy, call this I1. Call the second step I2. I2 for every element is greater than I1. And the reason why is twofold. M plus is smaller than M, so the electrons are closer to the nucleus. And then two, there's less repulsion of the electrons, so smaller orbit size, and then the electrons are fighting against that nuclear charge. Smaller size is really just a smaller size, less electron repulsion. So I2 always greater than I1. So this is always true for all elements in the periodic table. E should be false. Energy is released by an atom when it loses an electron. Losing an electron requires the input of energy, so electrons are held onto by atoms, so it takes energy. So endothermic reactions, not exothermic reactions for losing electrons. Question 6. Consider the following orderings. Which one gives the correct trend for increasing ionization energy for the loss of one electron from the indicated atom or ion? Okay, so we're looking at I1s. So aluminum, silicon, phosphorus are in, they're right next to each other on the periodic table. And so that this is the proper trend for ionization energy. So ionization energy that would increase for these three. It might drop a little for the next element, selenium, and then go up from there. So you might get a small drop here. So these should definitely increase. Beryllium, magnesium, calcium, strontium. We should get a slight decrease from top to bottom. So that's not true. We should get a slight decrease from top to bottom. So this would be true. So if we a decrease from top to bottom would have F higher, chlorine, bromine, iodine from there. And then what about the series of plus? So if we go from 10 electrons here, 10 electrons here, 10 electrons here, these all have 10 electrons. So if we have 10 electrons, having more protons will lead to a greater energy being needed to remove that next electron. So we go to sodium 2 plus or magnesium 3 plus. Magnesium 3 plus indeed takes more energy because we have a higher Z. We have 11 plus for sodium, but a 12 plus for magnesium. So those 10 electrons are held on to more strongly. It takes more energy for magnesium to lose an electron. So this trend here is true as well. So I got 1, 3, and 4 as being the correct answers. The only one not true is 2. What is the electron configuration of gallium 3 plus? The key for cations is go to the neutral atom first and just start with neutral, then lose atoms from here because I'll explain why in a minute. Gallium is don't have a periodic table right in front of me, but I think it's I want to close the window. I think it's yeah, it's right after zinc. I knew that. I don't know why I didn't trust it. So this would be an argon 4s2 3d10 4p1. And so for cation configurations, we don't lose the electrons in the order that we put them into our atoms, or the way we thought we put the electrons into our atoms. We lose them from the highest N with the highest L first. So we lose the electrons from the largest orbitals first. We first lose electrons from the largest orbitals. So the largest orbital is the 4p, so we lose this one first, and then the next biggest orbital is the 4s. In fact, notice that these are the only two valence orbitals. And so it makes sense that we remove the outermost electrons before core electrons. So highest N with the highest L, so the 4p1 goes first and the 4s2 go next. So our configuration should be an argon 3d10. And so then some questions will get at, well, how many unpaired electrons does the atom have? And that's really just another test for if you have the right configuration. If for some reason you thought that this was a 4s2 3d8, then you might think this has 2 unpaired electrons, but you would say that this has 0 unpaired electrons because it's a completely filled d subshell. And this is an anomaly. This is the rule for all cations. Go to the neutral atom and then lose the electrons in the order of largest orbital. So in order of orbital size being largest first. So the electrons furthest away, least held on to, easiest to remove is the main idea. Finally, number 8, which one of the following is correctly ordered from smallest to largest in size? Okay, so magnesium, sodium, fluoride. This makes sense because we have 10 electrons each, and then we have 12, 11, 9. So 12 protons being smaller. So A looks like it's correct. B is incorrect because fluorine is not, F minus is not smaller than sodium plus. So F is smaller than sodium, but F minus is greater in size than sodium plus. So you got to compare your isoelectronic series, and then these are nonsense here. Okay, so that's a few questions that hopefully get us either reviewing chapter 7 on Tuesday or introduced to some ideas on chapter 7 on Thursday. Some of these problems could be skipped, so your TA might skip some of these problems and look at them maybe next week. But just like we had um, for before midterm 2, we just have to make sure that all the recitations have a chance to see basically 4 activities between now and the next midterm. And so we just got to kind of pick up the pace and realize that, when we get to that last activity before a Wednesday night exam, then we're going to be doing some problems either ahead or then catching up with the class as we go along. So just check the video if you don't get the problems in class, and use these problems to help better understand lecture examples when we get there in lecture, or to better understand homework problems when we get there in the homework. All right, guys, have a great day.